Okay, so now for the next talk, we have Chris Osborne, who is a postdoc in the School of Astronomy and Astrophysics at the University of Glasgow. And he is currently applying machine learning techniques for the analysis of spectroscopic solar flare data with this literature. And Chris previously did his PhD in the same group, focusing on numerical modeling and interpretation of solar flare observation, primarily considering optical radiation that form outside of the local dynamic equilibrium. So,
thank you for that, and thanks for giving me the opportunity to speak here today. So, I'm going to talk a bit about our approach to solving a relatively complex inverse problem and how we managed to sort of use neural networks to make that easier. And in fact, practical at all. So, to start with, what sort of data do we have, since we need to understand data to understand how we're going to think about solving any of these problems. So the sort of data we get are images. We point a telescope at the sun and we have a camera on that. However, they're not just images in color. These are multi-wavelength images typically. So for example, in the top, we're imaging a spectral line, and we'll have 25 images across that at different wavelengths very closely spaced together. And then for, say, another line, say at the bottom, we have about 15 wavelength points across that observation. So, and these spectral lines tell us a lot of information about what's happening in the atmosphere. And what we want to find out, is so what are the parameters of the plasma in the solar atmosphere that we're looking at? And this is particularly difficult to do for flares, which are these sort of very short, rapid, explosive events that dramatically change. So we see these really bright glows popping out, and the plasma evolves on the timescale of minutes. Our observations are taken on the timescale of about every 10 seconds. So we get a good idea of what's going on, but we also know from our models that the evolution timescales of sort of what we consider an individual pixel, which here would be about 50 kilometers across, is probably actually well below a second. So we have a quite poorly resolved problem in the time domain as well. What do we want from this? So I've marked a couple of points on the image with a circle and dot. One is on a flare ribbon, and one is what we're going to loosely term as quiet sun that's just sitting there. What we want is an idea of the atmosphere at these points. And this is actually an example of what our model is going to give us at the end. So we're interested in primarily what's the electron density through as a stratified function of height throughout the atmosphere that we're looking at. What's the temperature, and how fast are things moving? Are there flows? Is it flowing up? In the case of an eruptive event, we expect a significant upwards motion at a few hundred kilometers per second. In the case of quiet sun, we expect it to be relatively static. So, how have we done this up till now before applying machine learning to the problem? So typically what we've done is we have some forward models that can take in an atmosphere and produce what we expect the outgoing radiation to be. And we can fit these using a relatively typical approach. We sort of define a model for the atmosphere, and then we perturb that model to see how the outgoing radiation reacts to those perturbations, and then we minimize that difference until we're happy with it. Effectively the same as training a neural network. These models are exceedingly expensive. The cost of doing more than pixels will take on the order of a few CPU minutes to do one sample for a pixel, and to actually determine a plausible atmosphere for a pixel, we're looking at a few thousand samples typically. So to consider inverting megapixel images, we're looking at supercomputers for days to weeks. And then we have a time series of those images every 10 seconds for multiple hours quite often. And obviously we can take that data whenever the sun is in the sky. So we have a huge data problem and computationally no easy way to solve it. So what's the main issue with solving this problem? The biggest issue with this problem is that we lose information. The line profiles alone, what we observe does not capture all of the information that is present in the atmosphere. there is no unique solution from which you can go backwards to recover an atmosphere from what you're observing. And so in that sense, we need to reframe the problem to apply these new machine learning models to it. So at the moment, the approach where effectively we're fitting is that we start from some line profiles, and then we start from a guess of the atmosphere, and then we just tune that until we get close enough. And you can't prove that what you found is a unique solution. And in fact, you can often prove that it is not a unique solution. So at that point, how do you disambiguate between them is a problem. Instead, what we do is we say, okay, we know that there is information lost in this process. So we're going to define a latent space where this information ends up. And instead of mapping between atmospheric parameters to the line profiles and being unable to have a injective map backwards, we form a bijective map between the Cartesian product of this latent space and the line profiles together to the atmospheric parameters. So that way there is a nicely well-conditioned bijective function that we can consider learning with a function approximator, like a neural network. And yeah, therein lies the issue. Effectively, these models can only be used for regression and classification. In the basic sense, we have a feed-forward neural network. It's a function approximator, and it approximates effectively, typically just a regression problem. They're not invertible in general, and there are generative models, particularly when we were doing this, were relatively young and solved a lot of problems with mode collapse, for example, in GANs, where you wouldn't know in advance whether the solution that was being learned was the average of two valid solutions if you had a degenerate problem, or maybe it was just learning one and ignoring the other, and you couldn't guarantee that you were getting stuff out. So we wanted a more robust solution than that. I'm going to skip over that here because you all understand neural networks, I think. So there is a way, and this was some brilliant work originally by Dean et al., where they basically said, we can compose any arbitrarily complex function, doesn't need to be invertible, by using these affine coupling layers, which are explained either with equations or diagrams, depending on which you find easier to understand. We can compose those together and get a bijective function at the end. And so the great thing with that is that these functions can be arbitrarily complex. This whole thing, we can compose these all together in standard auto differentiation frameworks. And that whole thing is differentiable. Okay, we've got a building block for a network that can run in both directions. Because we make the individual S and T functions, we make those each individually deep neural networks, and now we've got a layer made up of 4 deep neural networks, and we can stack those and we can reverse forwards and backwards. So what happens is just we split the input coming in and then just perform that series of transformations and concatenate it again from the end. So there was a slight issue with just concatenating the information, which is that if we're splitting it in half each time and then reconcatenating it at the end, the information doesn't, we sort of end up with 2 channels of information and it doesn't really mix very well going through. So we just added some random fixed permutation layers between each of those stacked affine coupling layers from the previous slide. So this is sort of the final structure of the network we come up with and how we trained it. So the input are these stratified atmospheric models, and the training data there comes from some simulations that we have. And the output is what we predict the outgoing line profiles to be, what the data we started with, essentially the data we said we want to model. And we train this model both in the forwards direction and the backwards direction. And so going between these, the latent space here is drawn from so it's a 150 dimensional latent space with what we ended up settling on, and it's drawn from a unique Gaussian ball. And so these affine, and obviously the information that was lost in the problem isn't Gaussian in nature, but we can transform that probability distribution by stacking affine transforms to get something that is equivalent to the information that was lost. And that is the purpose, effectively, of these affine coupling layers, is to transform that probability distribution, which is quite similar to a lot of the work that's done, for example, in normalizing flows. But we need to make sure that it does actually capture that information. So to do that, we use a particular loss, which is the maximum mean discrepancy, which is effectively saying, if I take these samples drawn from one distribution and these samples drawn from another distribution, how plausible is it that they were drawn from the same distribution? And so we end up with 4 losses in that we need to have a classic mean squared error on both the input and the output when we're training forwards and backwards, but also we need to check these inter and intra-sample variabilities using the maximum mean discrepancy to check that our latent space is well conditioned. So yeah, it's trained on these one-dimensional simulations, which are not the best proxy for reality, but they are the only thing we have right now. And we will see some issues as a result of that. This is the standard in solar modeling at the moment. So checking that our model works, the input to it is this atmosphere at the top, in the top row, and we get a very nice low mean squared error. It can correctly reproduce these snapshots taken from our models. So the dashed line here is generated by the model overlaid on the expected results. The inverse, there we go. So the inverse of it, we're taking the line profiles now, and because we assumed from the beginning that we could have a possibly degenerate problem, we're looking at we need to figure out what a possible output distribution of atmospheres is. There is no single distribution. We start from the premise that this is degenerate. So we take multiple draws of the latent space when we're plugging in these atmospheres and going through the round trip. And then effectively we get a nice probability distribution. And we can see our spectral lines don't inform us equivalently everywhere in the information. Don't inform us, don't give us the same amount of information everywhere. So, for example, we see this wide band on the velocity plot at the end, and that's due to the fact that we don't actually have very good information there, so it's unsurprising that it's less well constrained. So our model physically makes sense in the predictions it's making as well, which is always good. I'll just skip through these. The real data ended up coming out noisy but plausible, well constrained, and matching analysis people have done of this event using traditional forward-fitting models. And what it lets us do instead of analyzing 2 or 3 pixels is instead apply this to a whole image in a matter of minutes. And so now what we've actually got is a slice through a predicted atmosphere at a particular depth for the parameters which we're interested in. And so this really lets us do much bigger scale analysis of this data than was previously possible. I'll finish up there. So this is a very interesting technique, but it's still in quite early development. I think most of astronomy is interested in this sort of inference problems where we have only remote sensing observations. We have no way to measure what's going on, and we typically have some kind of information loss between the thing we're looking at and the actual model. There are newer approaches in this kind of invertible neural network. Like everything else, they've gone conditional now. But they do seem to struggle with very high dimensionality is the problem that we've been dealing with here, since this is sort of a 200-dimensional problem when we're dealing with all of the spaces in the atmosphere. That's all. Thank you. Yeah.
So do you have any questions in the audience? Okay, we do.
You said settle on 150-dimensional latent space, and I think the motivation for using the affine coupling layers was to give you this bijective map. So is 150 the difference in the degrees of freedom of the input versus the degrees of freedom in the output that you're interested in, or like how can you? Is that something you can choose, or
the 150 was it was tuned. but it ended up actually being the size of the input. And so it is likely that not all of those dimensions are actually used or used efficiently by the model. You could likely compress that because obviously if the latent space is the same size as the input, that's assuming that all of the information can be lost, and obviously all of the information isn't lost.
So how can you have I suppose it can still be bijective if it's larger than
It's just an inefficient mapping.
You can make it smaller than the input though, could you?
You can make it smaller. You end up with some zero padding in the network, engineering reasons, but you can make it smaller. We just found it learned most efficiently at 150.
Thanks.
Do we have any other questions? Okay, I think I had one. So if I understand correctly, you are essentially generating your training data from a simulation. And how do you evaluate the way that maybe when you observe events that may be very rare and that might not actually be predictable or fit in your simulation model? How do you make sure that you will be actually able to capture events that are essentially out of your training data distribution?
Yeah, that's absolutely a problem. We've put some other observations through this, particularly some rare, very much larger flares that we got data for, much more energetic events, and we found that the error bars on those sort of histograms generated from the latent draws got much broader, and so the model was much less confident in its own results. So it provides some sort of bound in that sense of confidence to at least say, okay, physically we need to look at this a bit closer.
Okay, thank you very much. I think if we don't have any other questions, we're gonna follow through with the next one. Thanks you again, please.